Told you about these Lorentz transformations. So if we are moving from one frame to the another frame, let's say you are doing this as a K frame and then you are saying K prime frame. Okay, so we can move actually along X direction with certain velocity, or we can move along Y direction with certain velocity, or we can move along Z direction with certain velocity. So if this velocity is introduced, okay, yes, we call them as a boosters. Okay, so we can be having three boosters along, let's say in X direction. So it will involve a time and X, and another we can have time and Y coordinate, another time and Z coordinate. Okay. So these are the three planes. So we can be having transformation between these three coordinates, is it? So if we are having transformation regarding to these three or in these three planes, usually we call them as the Lorentz boosters. Okay. Now if we are having, let's say, the transformation between xy, xz, or zyz, so these do not contain actually what? They do not contain time explicitly, is it? So there is no time involved. So these we call as the special rotationals. Lorentz transformations are in general boosters and rotationals. Okay, the usual Lorentz transformation, what you know, those are actually boosters along X direction. Okay, so let's do those boosters, then we can put a general form of the transformations. Okay, so we can actually resolve these transformations into these six planes. So in this four-dimensional space-time, we can be having transformation involving these set of coordinates. Okay, we can restrict either to xt plane or yt plane or zt plane, or xy plane, xz plane, or zy plane. Okay, so these are the restrictions what we can do. In general, you can be having an arbitrary point, okay, which is having all these xy and xy, z and t coordinates, and all get transformed when you move from one frame to the another frame. Okay, so that's most general kind of transformation. Okay, so but we will involve the boosters. Okay, so last time I told you that if you are having, let's say, this length, we will take only the two dimensions, x square plus y square. If you make a rotation of the coordinate system, okay, so you go from one coordinate system to the another coordinate system, length remains preserved, is it? So I am taking only two dimensions here. Okay, so you can generalize it to three dimensions or any n dimensions. Okay, what is the transformation that relates these primer to the unprimers? Okay, so you are having this kind of transformation, let's say, so which keeps this preserved. Okay, y cosine. Okay, so if you substitute for x prime and y prime here, you will get this back. Okay, so that means length of the vector remains preserved, is it? If you, so this is simple Euclidean geometry. Now the geometry what is under consideration is the length is given like this thing, c square yes. Okay, so the length what we know, ds square. So what is that? So the length of the interval is given by this thing, or ds square is equal to minus c square dt square. We can put like this thing. So we are having minus signs. Okay, either minus or plus. Okay, so one of the components or one of the terms here, okay, contains minus sign, or rest contains plus signs, or we can have like this thing. 3 contains minus sign and 1 contains plus sign, is it? So this length is entirely different than this length. So this length, okay, we usually, it's actually the pseudo-Euclidean or Mainkowiski, the length defined in the Mainkowiski geometry. This defines the Mainkowiski geometry, okay? We'll take only two coordinates. Let's take only two coordinates, what we call the ct and x, in tx plane, okay? So what would be the length of a vector? Huh? Yes, x square minus c square t square, is it? That will be the length of the vector from the origin. So let's say if you are having some frame of reference, this is the origin, and you take, let's say, some point which is having c, t and x. Okay, so this is x and this is ct. Okay, what would be the length of the vector in Minkowski geometry now? So it will be simply c square t square minus x square, or x square minus c square t square, depending upon the convention what you are using. Okay, so this is the general definition. Now what I want, so since the length of the vector, it's a scalar quantity, is it? So I want this length to be invariant or preserved under transformation. When you go from one frame to the another frame, the length remains conserved, is it? Sorry, constant, is it? Or it remains invariant, it does not change. So what does that mean? If you go from one frame to the another frame, it is like this thing. Minus x prime square, or you can put x square minus c square t square is equal to x prime. Okay? So it is the same kind of thing here. So you are having x square plus y square equal to x prime square plus y prime, except you are having a minus sign, is it? Now I want to define a transformation between x and t, okay, when you move from one coordinate system to the another coordinate system, such that this length remains invariant, okay, or such that this equation holds. I need to figure out what is the transformation rule between x prime t prime and x and t, is it? So the way we are having a rule, transformation rule, for this x prime in terms of x and y, and for y prime in terms of x and y. Okay? We need to guess that. Okay? So what is, yesterday we wrote it?
Lorentz.
Okay, we thought, okay, we can think this, okay, we can imagine an imaginary angle, okay, through which we can do the rotation. Okay, we have already exploited this kind of relation. Okay, if you use, let's assume, you use this very relation here, you will not get this object the same as this object. Okay? So, once you try to use this object here, you will not get this side equal to this side. Okay? It will not remain invariant. The length will not remain invariant. That means I need to figure out something more than these angles. Okay? So this is defined in the real space, cosine of theta and sine theta. Is it? Theta is real here. Okay? Now if I define it this way, okay, the most general form would be, if I write, let's say, x prime is equal to, let's write, what was that? Cosine of hyperbolic theta minus ct sine hyperbolic theta, and ct prime, that's equal to minus x sine hyperbolic theta plus, okay, ct cosine hyperbolic theta. Or in other words, we can write it this in this fashion as well. Okay, x is equal to x prime. That means you can just invert the transformations, because the transformation should be invertible. The way we are having here, you can express x and y in terms of x prime, y prime, is it? Is that true? Okay, so I can write like this thing, ct prime sine hyperbolic theta, and ct you can write as, okay, x prime sine hyperbolic theta plus ct prime cos hyperbolic theta. Okay, now you can check, just use like this thing. Okay, let's use this thing. You can check x prime square minus c square t prime square. Okay, let's check it. What is that equal to? So it will be x square cosine hyperbolic square theta plus c square t square sine hyperbolic square theta minus twice x ct sine hyperbolic theta cosine hyperbolic theta. Okay, then you are having minus sign here, c square t prime you can write. Okay, so it is x square sine hyperbolic square theta plus c square t square cosine hyperbolic square theta, then minus twice x ct sine hyperbolic theta cosine hyperbolic theta. Okay, so this term cancels with this term. Okay, so now take x square common here, so it is x square into cosine square minus sine square, okay, plus c square t square sine square. Okay. So this object is equal to 1. Okay. So this object is equal to 1 and this object is equal to -1. Okay. So that means the length is preserved. Okay. It is invariant under this transformation. So we have identified the correct transformation. You can similarly use this thing. Just put x square minus c square t square. You will get what? X prime square minus c square t prime square. Okay. Got it? So much ever? Okay. What is unknown here? So this is a transformation rule defined in xt plane. Yes, get it. Okay? Clear? Any question? Huh? Yes? Let's come here. So what we need to figure out? We need to figure out theta. Theta is unknown to us. Okay? Okay, now let's observe. Let's say frame K, unprimed frame. We observe the motion of origin. Let's say motion of origin. Let's say x prime equal to 0 of frame K prime. Let's observe the point x prime equal to 0 in which frame? In K frame. Okay? We are assuming here K prime is moving with respect to what? K at some velocity. Okay, here we have not defined that velocity, is it? Is it true? We have not defined it. We have defined there is actually there exists a rotation between K frame and K prime frame, and that rotation takes place through an angle theta, rather through an imaginary angle. If you put this cosine hyperbolic theta is actually cos of I theta, is it? Is it clear? Okay. So we can imagine it in that way. Okay. So now what I will use, I will just substitute x prime equal to 0 in this very equation. As simple. Okay. What we will get? So that means we are observing which point? X prime equal to 0 in K frame. Okay. So what it yields me? So it yields me x cosine hyperbolic theta minus ct sine. So what it gives me? So it gives me tan hyperbolic theta is equal to x by ct. Okay? So now what is x by t? What is x? It is a velocity. What kind of velocity? It is the relative velocity between the two frames. Okay? So we can write it simply as v by c. Okay? So now we have figured out the tan theta. That means we have figured out theta in terms of the velocity. Okay? Got it? Yes, we call this theta as the rapidity parameter. Okay? So it is known as rapidity. Okay? It is very important. This theta is very important in describing collisions between the particles. Okay? Okay, so now let's substitute it there. We will get. Okay, so what I need to figure out? Cosine hyperbolic theta and sine hyperbolic theta, you just use. So we will get sine hyperbolic theta is equal to v by c divided by root of 1 minus v square by c square, and cosine hyperbolic theta is equal to 1 divided by root of 1 minus v square by c square. Just divide the two, you will get v by c, is it? Okay? So just triangle rule, you know how to do all these things. Yes, any question? Okay, good. So what is our transformation? So x prime is equal to, so just use it. So it is simply x minus vt divided by root of 1 minus v square by c square. Okay, and t prime will be, I will just take the c out. Okay, I will just use t instead of c. Got it? So it will be simply, anybody? T minus v by c square x divided by root of 1 minus v square by c square. So these are the transformations what you know. So y and z are here fixed. Clear? So y and z do not change. So these are the Lorentz transformations. Okay? So these type of transformation you already know. Okay? We call these transformations as the Lorentz boosters. So this is a boost along x direction because okay, you have actually made x direction. Okay, you are making motion along x direction. So you can have similarly along y direction. You can keep, let's say, x and z fixed, you can be having a boost along y direction, okay? Then this object will be what? Y prime is equal to y minus vt. Got it? Okay, so now let's try. So we have, therefore, boost along x direction, like this thing. So let me write x prime. Then, okay, let's write t prime first. Okay, then we can put, let's write ct prime. Then I will write x prime, y prime, z prime. So I can write it in this fashion, in this matrix form. So what is the term here? I am taking ct. So it is 1 divided by, okay, let's define our objective. Beta is equal to v by c. That will be simply tan hyperbolic theta, okay? So let's write gamma is equal to 1 divided by root of 1 minus v square by c square, okay? So now tell me what this factor will be here. So it is 1 divided by this object, it is gamma into x minus vt. So I am looking at this very term. You multiply c here, it is ct prime, ct, okay, divided by this object, that's gamma, is it? So what this will be? It's simply gamma. Then you are having v by c only. I have taken one c out. So it is minus beta gamma 0, 0, like this thing. Gamma 0, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So these are what? This is y coordinate and this is z coordinate. These are fixed, is it? Everybody followed it what I have done? I just relabeled, okay, I renamed the parameters. These are actually the standard definitions. So this is ct, this is x, this is y, and this is z. Now look here, so this is actually a 4 by 4 matrix, is it? In 4-dimensional space time. So you are having, I can think this ct, x, y, z as the components of some vector, some radius vector, let's assume. Okay? We can think it as the vector of some point with respect to origin. Can we think? The way we are defining any vector, okay? Okay. So you are having this object, let's say x, y, and z. How we, okay, if I have to define the vector R with components x, y, and z. Okay? So I can similarly define a new vector here, okay, which is having a component ct, x, y, and z. Okay? Usually we define it as a radius vector, okay? It is having how many components? 4 components, okay? And it transforms it in this way. So you can think these are, okay, this is actually the transformation rule through which the components of this vector transforms, okay? Or the way we defined earlier in this mathematics, you can consider a basis set and how the basis transforms, is it? According to the transformation rule of the basis, you can define a given set of the vectors. Is it clear? Is it clear? So I can assume this as, okay, a given coordinate set or the given vector or a given radius vector for which the coordinates transform in this way. Let's assume along the x direction. I boost along x direction, they transform in this way, okay? Then I can define various quantities based on this kind of definition. How a given quantity which is having 4 components transform under a given Lorentz transformation, okay? Got it? So this will serve as a definition for defining more general quantities. You got my point? Okay, one more point here. Okay, now look here. So these 3, okay, this 3 by 3 matrix defines actually x, y, z planes, is it? Is that true? And but these coordinates define only what? It contains time. So this is tt. Let's assume this is t, this is x, this is y, and this is z. Okay, so that means what? So this contains time and special coordinates. So this is actually t, x, t, y, t, z planes, is it? So that means these very components, okay, if I am defining this way, the element here, the first element, so this will define actually what? boosts, is it? And since these are purely special coordinates, they do not involve what? Time coordinate, is it? So the transformations between these very coordinates we call are simple rotations. Got my point? Samajh? So in other words, a Lorentz transformation we can define as boosts plus rotations, okay? So that in general cannot be as simple as this. So it can be having many terms, many complicated terms in this very matrix. Samajh? Okay, let me define. Let's assume this as okay, so let me write this. So this is a vector which is having components C, T, X, Y, Z, okay? So under Lorentz transformation then, so it transforms like this thing, some matrix, a matrix M which is a 4x4 matrix, okay, acting on some old X. The component, it will be of this form, is it? Samajh? Clear? A more general Lorentz transformation would be of what type? So it will be a 4x4 matrix acting on the unprimed X, is it? Giving us a new a primed X. Clear? Any question first? Any question? No, have you got it? Just tell me. Have you got it? Have you got it? Huh? Shall I proceed? Okay. Okay, so let me write a vector, the components of which I can define. Okay, let me write this way. X0 as the zeroth component, which zeroth component means the time component. I will define this as CT. I will use now this kind of notation. X1 is equal to X, X2 is equal to Y, and X3 is equal to Z. I will use this notation. X0 means temporal component, X1, X2, X3 means X, Y and Z components. Okay? Got it? So this is our definition. So this is not a power, these are labels, you know it. I already told you what kind of labels these are. Okay, for the time being I will just keep them as labels. I will distinguish between different types of labels later on. Okay? So therefore I can write, okay, a vector, this very vector. So it is having components. Okay, let me write first. You are having CT, X, Y and Z. Okay? So I will write it as X0, X1, X2, X3. Okay? Samajh? Clear? Okay. So I will write it as in this fashion, X mu. I will put an index mu here. Okay? An upper index. Samajh? Just it is simply the labeling of these components. X0 means this CT, X1 means X, X2 means Y, X3 means Z. Clear? It is simply the labeling. Now how these components transform under, let's assume these boosts. Tell me. Okay, let's rewrite first. So you are having this CT prime is equal to, when you say CT minus V by C X divided by root of 1 minus V square by C square. Since we have used what? Beta is equal to V by C, gamma is equal to 1 divided by root of 1 minus V square by C square. This you know, okay? Now tell me what is CT our? CT I have defined X0, is it? So this I can write gamma X0. What is V? So it is beta. So it is X1. So what this will be? X0 prime. Got it? Samajh? Okay, so now let's write this X1. So I will be having X as, what is that? X minus Vt divided by root of 1 minus, X prime, V square by C square. How I can write it? So so I will write it X1 prime is equal to X1 minus. So I will divide this V by C and multiply C. So V by C is beta, Ct is X0. So it will be beta X0. So gamma I will write this way. And let's say X2 prime is same as Y is same as Y. Okay? X3. This object. Okay? So now we are, okay, for example, under boosters, the components of this very vector, okay, so I'm having a vector having 4 components, okay, I take a vector with 4 components, of which the components transform in this way under Lorentz transformation. Okay, we will consider only this restricted class of Lorentz transformation. Okay, now if I take in general any quantity which is having 4 components, let's assume, let's take a quantity having 4 components, okay, if that transforms in the same way as the components of this vector x, okay, then we call that quantity as a 4 vector. Or in other words, okay, x mu here, it serves as the definition for a 4 vector. Okay, or okay, let's write. Okay, if you are having, let's say, quantity A, it is, okay, let's write A mu here, A0, A1, it's having 4 components, A3, okay. If all these components transform in the same way as the components of x mu under Lorentz transformation, then I can say this A mu forms a 4 vector, or the A0, A1, A2, A3 are the components of a 4 vector A. Samajh? Now this is actually little bit different than the usual tensor of rank 1. We have defined tensor of rank 1, is that true? But if you see in those quantities, tensor of rank 1 is our vector, is it? So all the components are, I mean, on the same footing. If I define the length of the vector or the tensor of rank 1, so it will be the way we define in the Euclidean space, is it? Is that true? So let's say A upper 1, A lower 1 plus A upper 2, A lower 2, is it? So this way we define the length of the vector. But here, why these 4 vectors are, they are, I mean, peculiar in a sense, because there is that minus sign arising. The way we define the length of an interval, length of the interval consists of what? Few terms are of positive sign, another are what? Negative sign, is it? So that that distinguishes between the usual notion of the tensor of rank 1. Okay? So, but the geometrical properties of these various objects are the same, same as we define the tensors of rank 1. Okay? So, only the way the length of the vector is defined in a different way. You got it? Clear? Okay. So now let's take this as a 4 vector. Okay. So I can, okay, usually the upper index we write as the contravariant index. Okay. So I need to figure out what would be the covariant counterpart. If I am starting with a definition of a contravariant like this thing, what would be covariant one? Is it? For that, if you remember what we need, metric tensor, is it? Is that true? So we go from, let's say, if I am having a covariant 1, you multiply it by how many? When you say G mu nu A nu, is it? So you sum over mu, okay, so this mu will be lowered and replaced by nu here, is it? So what I need to figure out? The G. Samajh aaya? Okay, where from we get? So let's take the length of the interval. What is ds square? C square dt square minus dx square minus dy square minus dz square. Is there any cross term between x and t in this very length? No. So you are having you don't have any term between xt, xyt, is it? Or xy, xz, is it? Is that true? We don't have that kind of thing. What will be g? Now tell me, what will be g mu nu? When you say, what is the first thing? Plus, is no, it is c dt is one thing, it is length. Look, dx is the length, dy is length, dz is length. What c dt is? Length. You cannot take time as the length, c times t is the length, so what is the value here? 1. So it's plus 1. So rest are 0, like this thing. So what is here? Minus 1, 0, 0. 0, minus 1, 0. Okay? So this is one way to look at, so this is our metric tensor. So we'll use, okay, we'll use, because we have started with the notation of G, is it? in many books you will see actually the flat in flat space time geometry, it is represented by eta. Okay, like this thing. So many books will be using this notation. You should not confuse yourselves with that. Okay. So there is another way. Okay, let's try it. So you can be having another choice. D square is equal to minus c square dt square plus dx square plus dy square plus dz square. Is it? This is also the choice? Is this the choice? Okay, good. So what is g here? Tell me. Minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0. Okay? So that means we are having two choices of metric, is it? What to use? It depends upon your use. How you use it. So our convention in usual classical electrodynamics or in quantum field theories, we use this kind of metric. You got it? Which is having special components as negative. Okay? So you are having minus 1, minus 1, minus 1. Okay? So if you add these things, okay, what will be the result? What is the addition of these diagonal terms? How much is that? So the addition gives me the minus number, is it? So we call it as a negative signature. Okay, or in other words, if you are having more number of minus, that gives me the negative signature. This is one way to define the signature. What is the addition? Positive. So it is a positive signature. Okay, so many people often define signature to be the sum of these diagonal terms. If it is negative, so we call it as a negative signature. If it is positive, it is called a positive signature. But certain books define it in this way, but we'll use that kind of signature. If the temporal component is negative, so you call it as a negative signature. If the temporal component is positive, we call it as a positive signature. Okay? Got it? We'll define it in this way. What is the value here? Okay? So if I am taking negative here, then it comes with a minus sign here and all are the plus. But we will be using this thing. So plus here and negative here. Okay? If you use, let's say the upper one, results are still same. So it depends upon then how you choose the definitions. Okay? Got it? Okay. So now let's calculate these objects. Okay, so I am having this 4 vector as CT, X, Y and Z. Okay? So what is that equal to? So it is X0, X1, X2, X3. What is the inverse of this G mu nu? So the inverse of this we have studied. So inverse of G mu nu is what? So G mu nu upper. So it is the inverse. You remember we have done these things. G mu nu, G, let's say nu lambda, that's actually equal to nu lambda. Is it? So this we have already done. Okay. So now let's calculate this X mu. So what that will be? G mu nu X nu. Clear? Teacher, let's calculate the covariant counterpart. I start with the definition like this thing. Okay? So let's calculate the covariant part. You can fix covariant and calculate the contravariant. There is no problem. So what is this X0? So it is G0. Okay, so let's calculate it first. So this is X mu, G mu 0, X0 plus G mu 1, X1 plus G mu 2, X2 plus G mu 3, X3. Okay? So calculate now X0. So mu is equal to 0. What you will get? Now look here. So you are having G00, 01, 02, 03. Is it? 001 is 0, 02 is 0, 03 is 0. Is it? So you will be getting only G00, X0. What is G00? 1. So it is simply X0. So that means X0 lower and X0 upper, they are the same things. Okay? So there is no sign change. So samajh aaya? So that's equal to CT. So now let's calculate X1. Okay, from this let's calculate X1. So when you put X to G10, so this is 0. it will be simply G11 x1. Okay, so what is G11? Minus 1. So that means if you, okay, if you lower down, okay, look here, if you lower down the temporal index, 0 is the temporal index, is it? If you lower down the temporal index to the covariant one, is it? So you don't encounter a sign change, is it? There is no sign change if you lower down the temporal index. Now if you lower down the special index, 1 is a special index, is it? So what you are getting? So that means x1 lower is equal to minus x1 upper, okay? So that's equal to, so I can write it as simply minus x. Similarly, if you are having, let's say, x2, you will get minus x2, that's minus y, x3 you will get minus z. Okay, so therefore you can get this x mu as ct minus x minus y minus z. Okay, got it? So much, Shivan? So in our signature, what we are using, if we are using this kind of metric, okay, look here, if we are using this kind of metric, what happens? The temporal indices, if you lower down or raise the temporal index, you don't get a sign change. But if you lower down a special index or you raise the special index, what you will get? Sign change, is it? Got it? Remember this very point. Now how we define the length of